Hey, welcome to Gold's Garage. So a month ago or so, my son Michael and I made a trip to Winston-Salem, North Carolina, and we visited Brian Hambley and Galen Biggs at Forsyth Community College. And I made a video at that time for Brian's class of 2024 on the subject of fasteners. And so at the time, we didn't really have a chance to make introductions. We just started the video in progress. So thought we'd just cover this off. So Forsyth College has a program for race car engineering. My good friend Brian was a NASCAR engine builder for something like 40 years. And he's semi-retired. He still works for Pro Motorsports, but he's also working during the season for Forsyth Community College, teaching a number of things, including engine building for that class. So Brian invited me down. We've kept in contact over the years, and we visited back and forth a few times. And so Brian invited me down to talk to his class about the subject of fasteners. So what you're going to see next, we're kind of jump right into it, is my my presentation. So if you're interested in fasteners, you're going to enjoy it. And even if you're not, you might get interested. There's probably things. Fasteners are the number one cause of mechanical failure in industry, and probably one of the major causes of engine failures as well. They're one of the most important parts of an engine, and they're one of the most misunderstood. And that's why they cause so much trouble. So hopefully you'll find this is actually a video. My son did the camera work for me of the actual presentation. Hope you enjoy it. Thank you for watching. Please like and subscribe, and the next clip will have the presentation. Okay, we're going to go and meet the students here. We're just getting started. So,
everybody got their program shirts on? Morning, class. This is Alan Gold, Gold's Garage, his son Michael.
how are you guys?
He's here to do a presentation on fasteners, not just for motorsports application, but all fasteners are similar in application, use, and design. So Al is a mechanical engineer. He actually does design of steel mills, and he retired from the steel mill I worked at for 11 years after running the whole place, 12,500 employees. He was in charge, so he's a take charge guy. So listen up. He's got an excellent presentation on fasteners.
Thanks, Brian. And welcome, YouTube followers. We're on YouTube, guys, and we're live here at Forsyth Community College. And thank you, Brian Hambley and Galen Biggs, for inviting me here today. And it's my pleasure to talk to you guys, and we'll have a handshake and get together with each one of you when we're done. So we're here to talk about fasteners. Brian asked me to do that. I got a bunch of little prompts here to keep me on track. And as we go through it, we're going to cover a whole bunch of things about fasteners, some that you need to know, some that you might like to know. I do have a little point to make with you guys. If you want to learn something, don't just memorize it so you can pass the test, because you will forget it the day after. Take time to understand it. If you understand it, you own it for the rest of your life, okay? So, a guy named Einstein once said, I don't even know my own phone number, but I know how to find it, right? So if you understand something, you can figure it out yourself, and then you're going to own it. So I'm going to talk about, cover the whole gamut of it, what bolts or fasteners are made of, what steel they're made of. I'm going to use my old, this is actually just a short connecting rod off a 400, just a junk rod. I threw the other 7 away, but I'm going to use that for show and tell to explain a bunch of stuff. The rod is made out of almost the same steel as the fastener is. We're going to talk about that. I got my Waddell Wilson book. We went to the, my son and I, Mike is here with me, by the way. I forgot to mention that. He's on tour with me. We're going to actually Osprey Custom Cars tomorrow. I built an engine for those guys there in Wilmington. And I built a Blue Flame 6 for them about 4 or 5 years ago. So we're going down there to see Ron Siriano there. And anyway, we went to the museum yesterday because we got here a day early, so we wanted to do something.
We saw this in the museum, only a nice clean copy of it. This is the Waddell Wilson book that he wrote probably somewhere in 1970s, something like that. And I bought it in the 1970s. As you can see, it's been well used, right? So I got my CT400 manual to talk about. I got a little sissy torque wrench to just talk about the methodology of torquing. And we're going to get into the LS stuff, torque to turn, torque to yield. Why do they make you, when you take an LS apart, buy all new bolts? Just because you want to sell your bolts, or what? What's the deal with that? So we'll get into that as we go through. But before I get started, I got to talk a little bit about Brian. I'm going to tell you some stuff you probably don't know. So Brian and I go back a long way, back in the 80s, and we have some things in common. As Brian mentioned, we both worked at the same steel mill. He left. I stayed there for 34 years. And I was just getting into circle track racing when Brian was leaving. I was a drag racer originally. And Brian was a circle track racer. So we never raced against each other. We never raced at the same time. That's probably a good thing because we're still friends, right? So that worked out pretty good. First circle track car I ever drove, Brian had a dirt car down in Michigan someplace, 1982 or something like that. And I went down there, he let me take a couple laps in it. They were probably pretty ugly laps, but it got me hooked on circle track racing, and I bought a Junior Hanley car. Everybody ever heard of Junior Hanley? Everybody know who Junior Hanley is? So he was a pretty good circle track racer from Canada. So, and I went circle track racing for a number of years. My son Michael followed behind me 20 years later, and he won 3 championships, 2 in Michigan and 1 in Ontario with a super late model. So that's kind of the history. So there was a couple of stories about Brian. So when he's quite a bit younger than me, when he was a pretty ambitious guy, and this is the folklore from up in Canada. I didn't see this myself, but he wanted to go circle track racing, and he went down to Michigan and bought a car from Ed Howe. Is that right, yeah, Brian? Yep. And didn't have a trailer, so he borrowed a trailer. He got it back to Canada. Didn't have a workshop, so he set it up in a shopping mall parking lot. And he went out and won a race. So got off to a pretty good start, and he got well known. And he got offered a ride with Harold Ross Racing, and Harold Ross was the top engine builder in Upper Michigan, Northern Michigan. One of my mentors back in the 60s, Harold taught me lots about engines. And Brian and Harold won lots of races together before he left. And then he left and went to Grand Rapids right around the time I was starting. Worked for Paul Gianlozzi, right?
Yeah, 5 years with Gianlozzi's Trans Am team.
So I think he started driving the transport. He ended up building the engine, so in the engine shop. So if you think small block Chevy is complicated, try building one of those guys, 150 cubic inches and 800 horsepower or something like that, right? Something in that area.
The IndyCar motors were the worst. The 4-cam aluminum motors.
So that's what he cut his teeth on, basically, with engines, right? So lots of history there. And so back to fastener. So the job of a fastener, first of all, a couple of really basic premises is the job of a fastener is to create a clamping load between any 2 parts that is the force of that clamping load, strain energy that goes into that clamping load is more than any force that it's going to see when the engine's running. And that's the idea. As long as that's the case, the fastener will never see any more force than that. So the basic premise is when you torque a bolt, and I'm going to just use my little torque wrench because they're easy to carry, the amount of force, the amount of torque, the amount of strain energy that goes into stretching a bolt is proportional to the energy you put into it. So Newton's law of energy conservation said energy can either be created or destroyed, but can change its form. So if you torque a bolt, whether it's a grade 2 bolt, a grade 5 bolt, grade 8 bolt, a 250,000 PSI bolt, it'll stretch the same amount, it'll have the same stress in it, it'll have the same amount of clamping load. Doesn't matter what kind of a bolt it is. So let's talk about modulus of elasticity. I'm going to use, I only have one little prompt like this. It's a stress strain curve, and this is not something I made up. This comes out, this is the CT400 manual, so you guys, everybody knows what 604 is. 604 crate engine, probably the most common crate engine in circle track racing where we come from, that's all we use, mainly for circle track racing. So this is actually the spec out of that manual. So the basic premise is when you apply any material, whether it's steel or aluminum or plastic or carbon fiber, when you put a force on it, it'll stretch proportional to how much energy you put into stretching it. Okay, so this is a stress strain curve out of this manual, and this is stretch on this side, and this is the amount of stress you put in it, the amount of torque you put in it. So that's 10 foot-pounds, 20 foot-pounds, 30 foot-pounds, 40 foot-pounds, etc. And that's 1, 2, 3, 4, 5, 6 thousandths of an inch of stretch. So if you look at the manual, it says torque. And one of the things I guess I got to point out is there's a lot of important bolts in your engine. The most important is your connecting rod bolt. That's why I'm going to talk a lot about it. The next is your main bearing cap bolt. The next is your cylinder head bolt, right? And they're all important, but those three you got to get right or you're going to have a bad day. So when we get back to the bolts, so for the CT400, right out of the manual, it says torque to 45 foot-pounds, or if you're measuring stretch with a stretch gauge, everybody knows what the torque's connecting rod stretch gauge is. Stretch it to 6 thousandths of an inch. So that defines the curve of the stress to the modulus of elasticity of steel. And whether it's grade 2, grade 5, grade 8, or whatever, if it's alloy steel with carbon in it, it'll have the same modulus of elasticity. It's going to have the same curve to that line, okay, following this line. So when you put torque into it, it's going to stretch proportional as it's doing that. Can you guys over there see in that corner? You want to sit over closer maybe so you can see? Because we put this maybe in a bad place in a way. So it's up to you, but you maybe see better. Because this is an important premise. If you get this, you got it. This is the main thing you have to remember. So as you stretch it, okay, it'll elongate. And when you take that stress off, as long as you don't get to that line, okay, it's going to unstretch. Just like, so what do you think this is? Anybody recognize this? This is the spring out of the secondary of a Holley vacuum carburetor, okay? So the idea is a bolt is just like a spring, a stiff spring. If you stretch it, it wants to come back to this length it was before, and that's what is holding your engine together when you're revving, right? So as long as you don't stretch it too far, and when you stretch it too far, you reach what's called the yield point. And I've actually plotted two bolts. This is the CT400 connecting rod bolt. And this is a higher length, like a 200,000 ultimate tensile bolt. So you hear that term all the time. So many, 150,000 PSI bolt, a 200,000 PSI bolt. So we'll get into the definition of that, but the PSI is pounds per square inch. And that's usually the advertised number because marketing guys, when the marketing guys want to make it look better, they always give you the number that's the highest number the bolt can withstand. So this stands for ultimate tensile strength, which is basically the point where the bolt fails catastrophically. So that's a nice number and everything, and it's interesting, but you don't want to be going there with any fasteners because once it gets there, it's already failed, okay? So you want to stay on this line where it's straight, and if you reach the line, reach this point, let's say let's forget about the top for now. Let's look at this one. This is the bolt out of the CT400, okay? When it gets to this point, so up to now, you're adding torque. The energy you put in minus friction, we'll talk about friction, but the energy you put in is proportional to how much it stretches, okay? So it's stretching, and if you take that torque off, it'll come back down to here, and it's back to its relaxed state. If you keep going, okay, now it's going to be permanently elongated. So in this range, it's elastic. That's where you always want to stay. And once you get to this stage, it's called plastic deformation because the bolt, even though the stress goes up, it goes up because the bolt's actually necking down. It's getting smaller in the middle. This is a main bearing cap bolt out of Mike's. I'm building an engine for Mike's. I'm going to race a Michigan modified car this summer. And this is a bolt out of the old bolt out of his main bearing cap. So as long as you stay under this line, the stretch will come back. But if you go this far, and that's where you're going to get in, we're going to talk about the LS engines, stress torque to turn deal, and why you can't use an LS engine, because when you keep torquing them, they get into this range, and now they're permanently elongated. So up to this line, where the line is straight, it's elastic, and that's called elastic range. And in this state, it's called plastic, because visualize when you stretch a piece of plastic and you see it kind of turn white, it's permanently deformed. It's not going to go back to its original state. So if you understand that concept, stress, okay, which is torque, basically torque creates the stress, versus strain, which is elongation. Okay, so let's go for a ride in Mike's engine, just to give you an idea. There's a thing called fatigue, and fatigue is, even though if I take this little piece of, I think it was out of a coat hanger or something, and I bend it back and forth, I can bend it back and forth, it's not breaking, it's not failing. I'm down in this range someplace, okay? But if I do it enough times, it'll fail from fatigue. So just like it sounds, it gets tired, right? So every piece of metal has a fatigue failure point, and a fatigue failure point is a product of two things: how high you are in this stress line and how many times you stretch strain it. Okay, so make my point about bolting. So we torque the bolt to 45 foot-pounds, just like it's supposed to, put the engine together, and we go out and run for a season. So let's say we go 2,000 laps. I've been trying to make the math easy for myself here. The lap's 15 seconds, and we average 6,000 RPM a lap. So if you do the math, I already did the math, so I got it in my head. So 6,000 RPM, 15-second lap, it's only a quarter of a minute, right? So if you got 6,000 RPM, that's 1,500 times a minute. The engine's going to revolutions a minute. So what's going on with the engine? The bolt's torqued down. It's preloaded to 45 foot-pounds. It's stretched 6,000 7-inch. That's what's holding your main cap on. So every time the piston comes to the top, okay, it wants to keep on going, and that stretches the rod. The rod is made out of all carbon steels, all carbon steels have basically the same modulus of elasticity, whether it's a 200,000 psi bolt or a grade 2 bolt that's got 90,000 psi bolt. So the rod stretches, but the bolt doesn't, because it was already stretched when we torqued it, right? The piston comes to the top. It wants to keep on going, right? It doesn't want to stop. It has to stop instantaneously, start going the other way. It has mass, and that mass gives it inertia. The inertia that it has, the inertia force that it has, is the product of the weight of it and the square of the speed. So if it's going twice as many RPM, it's going to 4 times as much force. RPM is what kills motors, guys. So if you're going 6,000 RPM, the force on that rod is not twice as much as that 3,000 RPM. It's 4 times as much as that 3,000 RPM. That piston wants to keep on going. Now you go in the corner and you lift, you close your throttle plates. You got a big vacuum in the engine. Your headers are trying to evacuate the cylinder and just trying to pull the top off that piston, right? And keep it going. That happens. So Mike, in the season, 2,000 laps, 1,500 revolutions a lap, that happens 1,500 times. Piston's going around. Let's see, if I'm going that way, so it's going that way, right? If I'm going that direction, every time it comes, that happens to it. So the rod sees that stress 1,500 times a lap times 2,000 laps. Do the math. 3 million times in a season, that rod's going to stretch and strain. When it goes up, it's going to stretch. So when the spark plug fires, it's going to push it back down. It's going to compress it, right? So that's the force it's going to see 3 million times in a season. So anybody want to guess how many times the rod bolt's going to see? How much stress is going to be on the rod bolt? How often is the rod bolt going to see that stress? 1 time when you torqued it. Okay, you torqued it, you preloaded it, you put strain energy into it, and as long as when you torqued it right, you stretch it 6,000 of an inch, that the connecting rod bolt doesn't feel a thing. Okay, so at the end of the season, I build engines. You guys know that. Somebody said, "Well, let's change all the rod bolts. It's had lots of RPMs." Rod bolt doesn't care. Okay, rod bolt had only time it would stretch is when it was torqued. That's all. So if you remember that, and if the connection is done right, it should last almost forever. So, talk about fatigue failure, modulus of elasticity, stress and strain. So what is PSI? PSI is kind of a commercial thing. So all bolts we're talking about, I brought a couple samples here. You can look at this stuff after. I got a grade 5 and a grade 8 bolt. They all have a PSI rating. A grade 8 is about 150,000 PSI. A grade 5 is about 120,000 PSI. So the PSI is this point on the line. Just for relativity, by the way, this other line is aluminum. I said every material has a stress strain curve, has a modulus of elasticity. The slope of the line is depending on how stiff it is. So aluminum is obviously not as strong. So for the same amount of torque, aluminum would stretch like 20 thousandths of an inch, okay? Whereas steel is only stretching 6 thousandths of an inch, okay? It's a lot less, it's a lot stiffer, right? So it doesn't matter when you torque a bolt down, whether it's a 200,000 PSI bolt or whatever, but the PSI is pounds per square inch. So if you do the math, the cross-sectional area of the connecting rod bolt is, if it's a 3/8 bolt, is, I did the math, 0.11 square inches. So if you take 150,000 and multiply by 0.11, that's 16,500 pounds that bolt's holding when it fails, basically, when it finally gives up, okay? Once again, this is all interesting. It's all good for marketing. You don't want to be going there, okay? Even in an LS, 120,000 PSI which is the point of yield of an LS. I don't know what the LS bolt, but this bolt, the point of yield is 120,000 PSI. That's 150,000 PSI. So when you torque a bolt on a old school stuff, okay, the torque point of 45 foot-pounds is about 75% of the point at which the line starts to bend. And that's the safety factor. So you torque that bolt 75% and you untorque it. You can torque it again and torque it again because every time you torque it, it's only one cycle. The bolt can be reused. When you torque an LS bolt into this part where the line is red when it's coming back down, that's why you can't use it, because it's permanently elongated, okay? That's the idea of it. So, so if you're stuck with old school stuff, and by the way, torque to term, we're going to get into that. I'm sure you guys do that stuff, hey? You guys are all into all that stuff. I don't build LS engines, by the way, but I know enough to talk to you guys about them. That's not I build, as you probably know, old school stuff. But that's a better way to do it. But if you've been using the torque wrench all your life hasn't been wasted. Everything you've done is worthwhile. The energy you put into it is working, and an engine will still basically last forever if it's put together properly. Okay, so that's your yield point. So if you are going to torque, you have to remember some things. If you use a torque wrench to tighten stuff, and I build engines with torque wrenches all the time. I don't build LSs, like I said. And so you have to make sure, one of the biggest issues with torque wrench style tightening is when I just said Newton's law of energy, when you turn it, you put in so much energy, that stretches the bolt. Minus friction. That's a big factor. Friction, when you torque a bolt with a torque wrench, about 80 to 90% of the energy that you put into it is overcoming friction. Friction in the threads, okay, the bolt, and under the head of the bolt, typically. That friction is a lot, and it also makes it very difficult to measure. A colleague of mine up in Canada, Cutter's Performance, recently made a video. He makes videos too. He's got a good video channel. He lives in Ontario, Canada. And it's a very objective video, because I know we talk about ARP. By the way, I would say if you want to know lots about fasteners, ARP's got a great website. They got lots of technical information if you're interested in learning. But he made a very objective test. So he had a torque stretch gauge for measuring the stretch in a bolt. Okay, and he just took a regular connecting rod bolt, and I forget if it was an ARP or bolt on, but it doesn't really matter if it was. And he started off with 4 or 5 different, using no lubrication at all, then using oil, then using various other kinds of lube, moly, and whatever else. And after each application, he measured how much the bolt was stretched. So you're looking for 5 or 6 thousandths of an inch, right? And with no lubrication, it had almost like 1 thousandth of an inch of stretch. And the various things along the way that he used, none of them got even close. And he finally put ARP lube on them for the last trip, and he got his 5 thousandths of an inch of stretch. So I'm not here to sell you ARP stuff, but that's a pretty objective test that he did. It's a great video, Cutter's Performance. Check him out. And it's convincing that with ARP lube, measuring the stretch, he got the stretch he wanted. So it just shows you the problem with torquing. You have to make sure, first of all, that your threads are nice and clean, your cylinder head, the threads in the block are nice and clean. One of the things I do typically after I'm sure that they all are, I take my little impact. It's only 15 foot-pound impact and a rod head bolt. I go up and down every hole, and if it doesn't, my little 15-pound impact can't drive that thing right down instantly. There's friction in there someplace, and you got to get rid of it with a thread chaser or a tap or whatever. Clean out the threads. The joint has to be ultimately stiff. Okay, so you need to make sure. One of the things about friction is 2 soft surfaces have more friction than 2 hard surfaces. So you want to be using, especially if you're torquing a head bolt on aluminum head, you want to use a flat hard washer under the head of the bolt. That'll have a lot less friction. If you're torquing onto a soft surface like a cylinder head, it'll start galling the aluminum, and that creates more friction, and that takes away. The more friction you have, the less amount you're going to stretch that bolt. So that's really important. I don't know if you watched my video about lock washers. If you got lock washers in your bolt bin, go get them right now after this video and throw them all away, because they're going to get you in trouble. Lock washers are soft. If you like them because they make you feel good, if you're 1/4 inch or 5/16, you probably won't hurt anything. But in any torqued application more than that, more than 30 foot-pounds, they're going to just squash out and ruin your joint. So back to one other point about the fastener is an example like a connecting rod bolt. The limitation isn't just the fastener, it's the connecting rod too. So if you took this connection rod is designed for a grade 8 fastener, that's when you're torquing it, it's only 90,000 psi. When it yields, it's 120,000 psi. If you took a 250,000 psi, and you can buy these type of things, I'm going to talk about how they're rated later. If you took one of those bolts and you torqued it to this point, you would distort the rod and you would take away clearance, and you'd probably have a bad day because your oil won't have clearance in it again. It's not just the rod. It's not just the bolt. It's the rod too, or whatever you're connecting. You just can't, unless the connection is made for that, you just can't put a bigger bolt and torque it more. And one of the reasons that connecting rod bolts are so vulnerable, there's only 2 of them. There's more main bearing bolts and there's more head bolts, right? And you just can't make them bigger because they're part of the rotating mass, right? So you just can't put a great big bolt in there. You don't have room for them, for one thing. But the design of a bolt, the stress on the bolt that when you torque it, this is 90,000 psi. So if you go back to my 0.11 square inches, so the force is force times the area, pounds per square inch. So that's 9,900 pounds when you torque the bolt, each bolt. So the design of it is so that either one of those bolts should have enough strength to hold it. And that gives an engineering safety design factor of 2 to 1. If one of the bolts is strong enough and you have 2 of them, right? By the way, don't ever try one, okay? I'm not, it's just theoretical, right? But that's the basic design concept. So torquing information, life's not ruined if you're using a torque wrench. I still use torque wrenches. Use good torque wrenches. Make sure they're calibrated. Make sure you don't have friction. Make sure you have stiffness in your joint. Don't use anything soft if it's an important joint. If you torque any bolt, let's say you use this a flat washer that you got someplace, and you torque it down. If you take it apart and there's an impression on that washer, it probably, what happened is the energy that went into tightening the bolt didn't stretch the bolt, went into squashing the washer. So you want to make sure you don't do that as well, right? So talking about the bolts themselves, I can even pass them around. I'm sure you guys have seen this kind of stuff anyways, but identification. I didn't bring a grade 2 bolt because I don't have any. I don't use any. Grade 2, we call them garden variety bolts. They're 90,000 PSI. This is actually the equivalent of a grade 8 bolt, and I'm going to talk about the metallurgy of them. So a grade 5 bolt is kind of the minimum you want anywhere on an engine. So you can identify that by 3 radial lines, and they're typically 120,000 PSI bolt, and they're good for anything but a connecting rod or a main bearing or a cylinder head, right? So a grade 8 bolt is kind of the standard. They have at least 5 or 6 radial lines on a grade 8 bolt. And the metallurgy of the rod, the connecting rod and the bolt are not much different. They're all carbon steel alloy fasteners and material. They're very similar. So standard is around a grade 8 quality standard. This is grade 8. This is grade 8. They're usually shiny because you don't want to make you feel so bad about paying twice as much as it costs to buy one of these guys. And they definitely are higher quality. The ratings are based on SAE, Society of Automotive Engineers, or ASTM, American Society for Testing Materials. And those kind of numbers, grade 2, grade 5, grade 8, are standards. But marketing can call them anything they want. You can add a bolt, a super alloy, or whatever you want to call it, right? So they get away from the standards. But these ones you can look up in the standards and find that information. So torque to turn, okay, these guys. So what's the benefit of torque to turn? I just talked about the fact that when you torque with the torque wrench, 80 or 90% of the strain energy, the more energy you put in, the more it's torque. But 80 or 90% of that energy gets taken away by friction. And friction isn't that, because you can always pull harder, right? But you don't know because you can't measure it. That's the problem. So if you use an LS style, or not just LS, Hemis, Coyotes, all those kind of engines that use torque to turn methodology in the late 90s, all those engines came out, and they pretty much are all prevalent now. The difference is that friction is no longer a factor because you're actually torquing, you can measure the torque. So if take that's a good old connector rod bolt, 3/8 fine thread bolt, 24 threads per inch. So if you divide 24 into 1 inch, that's 41 thousandths. I already did the math, so I figured out before I got here, right? 41 thousandths. So if you snug it up, get it so you just take all the slack out of it and turn it 90 degrees. That's 1/4 of 41 thousandths, okay? 1/4 of a turn, 1/4 of 41 thousandths. You just stretch it 10.11 thousandths or whatever, something like that, okay? So torque to turn, total variable of friction and not knowing it is gone. You know exactly how much you stretched it, how you stretched that bolt. The only negative thing about that is if the joint is stiff, some of that energy could go into compressing whatever you're tightening. That's the other side of it, right? That's why you have to have the way you connect your rods. And if you look at a nice scat rods or eagle rods or whatever, they're nice and stiff. The bolt is totally captured. They use dowels and all various things to make sure that they're stiff. Okay, so that's the main thing. If they're not stiff, then some of that energy is going to get, instead of stretching the bolt, it's going to compress to whatever it's tightening. So that's the benefit of torque to turn. So torque to yield, what's the deal with torque to yield? All of a sudden, you follow that practice? If you take a LS apart, you change all the fasteners or not? Are we doing that?
We replaced all the fasteners with ARP.
Yeah, very cool. So you're not reusing LS head bolts and stuff. Okay, so they don't do that just because they make you want to sell you a bunch of bolts. Here's the point of doing that. Back here with my good old school 604 engine, you're torquing the bolt to 75% of its yield point. So here's the best clue. How many head bolts in a small block shaft? 17. How many head bolts in an LS? 10. That's the answer right there. You're trying to get more work, more energy out of every bolt. So on a small block Chev, you stop torquing there, and you only use 75% of the strain energy available from that bolt. On an LS, you torque it to yield, and you use 100% of it. So you need less bolts to hold down the same head. In fact, LSs have higher cylinder pressures than old school Chevs, old school engines though. Talking about Chevs here, because I do mostly GM stuff. Sorry about that, Ford and Dodge guys and all that. But it's the same methodology, the same analogy, whether you have a Coyote engine or a Hemi or whatever, same deal. Okay. If you're using torque to yield bolts, what happens is they go up there, they stretch a couple thousand. So when you take the torque off, they come right back to where they started, and now they're 2,007-inch elongated. I think the rule is if you measure a bolt and it's a half a thou longer than when it was new, you should throw it away because it's already failed, essentially. So torque to yield is expensive, but so on the cylinder head, okay, you got a lot of things have to happen. You got to get air in and out. You got to get water in and out. You got a place to drain the oil. You got to have a place to get your push rods through there. There's a lot of things have to happen in that real estate. So if you can get away with 10 cylinder head bolts instead of 17, that's 7 less bolts, 7 less holes, 7 less things you have to worry about in your casting. Makes the head smaller and lighter and gets the job done. So less bolts, higher stress, gets the job done with 10 bolts versus 17 bolts. So the other thing, I'll give you a little bit of metallurgy. Guys, if you're looking at buying rods and stuff from Eagle or SCAD or these guys, one of the best 4340 rods. We want to use 4340 rods. What's the deal with that? So on any SA rating number where they use the 4 numbers, because then once again in marketing they can call them whatever they want, but the 4340, 4140, 1040, the last 2 numbers is always the carbon content. Okay, the more carbon you have, the stronger the bolt's going to be, stronger the bolt or the rod or whatever is going to be. The more carbon you have, the more brittle it's going to be. So you just can't keep adding carbon. So how steel is made, I got to go a little bit because I came from a steel mill, right? I worked there all my life. I'm not a metallurgist. So it starts with iron ore and coal or coke. Coke is just refined coal. And they mix together in a blast furnace. There's usually 1,000 tons in it at a time. They make about 7,000 tons a day. They mix metallurgically. And so cast iron, which your block is made of, the cylinder block is made out of, is about 3% carbon. And they call that pig iron. Pig iron isn't a bad thing because they can't sell it. It comes out of the blast furnace at 2,700 degrees molten. You can't sell it like that. They let it cool into these little shapes that look like a little pig. They look like a little small loaf of bread. So somebody called it pig iron. Steel is not iron, it's refined iron. So in the refining process, they drive out most of the carbon. So when it's a 4340 rod, it's 0.4 carbon, not 4%. Whereas cast iron could be 3 or 4% carbon. The more carbon it is, the stronger it is, but the more brittle it is. So the steel in the hood of your SUV is probably 1010 steel. So it's only 0.1% carbon. The less carbon, the softer it is, the more formable it is, the less brittle it is. So carbon's great. The other 2 numbers, the 43, represent the alloys in the steel. So alloy steel is expensive. So one of the molybdenum is one of the main alloys in almost any alloy steel. Chrome is another alloy, which is important to give. It gives it toughness. And when you have those alloys, the steel is more reactive to heat treating. So you raise it to a high temperature, you quench it fast, you anneal it after that, and that makes it tough and strong. So it's not fragile, it won't break easily. Okay, because you can't tool steel. Have everybody heard the term tool steel? It's a great product. It's used mainly for wear. Tool steel has about 0.8% carbon. So that's a lot of carbon. It's very resistant to wear. It'll last forever, but it's very brittle. You would not use a tool steel bolt in your connecting rod, that's for sure, okay? Because it would break, because it's not flexible. So a little bit about metallurgy, and I think I've pretty well covered it off. I talked about my Waddell Wilson book, old school stuff, and I don't know if you watched that video, guys. We get all this modern technology now. So in the 70s, he was using 60s. He was using 2-volt main engines. Almost all Chevrolet parts, original parts. Never had any aftermarket stuff. 7,000 RPM down the backstretch of Daytona for all day long, and they worked good and stayed together and made almost 600 horsepower. So it still works pretty good. And I am open for questions. Silence was a strong reply, right? Brian.
To put it all in perspective, the current Cup motors are 650 horsepower. So
yeah, they've actually come down. They were 800 or 900 at one time.
It's about longevity and cost saving.
Yeah, for sure. Yeah.
Once the gear rules went in place, cut the horsepower back, motors can last for 4 races now. Where you were doing really good to get one out of it.
Back in the days when they were making qualifying, you were building qualifying engines. I visited Brian down here when he was He was working for a NASCAR shop back then. Forget who it was now. But you were building qualifying engines, I think, at that time.
Yeah, they were made to go 3 laps.
Yeah. Yeah, that's obviously that wasn't very economical, and so that became a big problem. But 650 horsepower is a piece of cake, really. To make that, obviously. But did they do that by actually measuring the power, or by limiting the things you can put into the engine that'll make that power?
Restrict the air intake.
Okay, yeah, okay. I know, and I don't know what you guys do in short track racing and Pro Late model, where we use these engines, where we race. If they think they get suspicious, they take your engine out and they dyno it. If it makes more than 440 horsepower, you're automatically disqualified, and then take it apart to find out what you did, basically, right? Because most of those engines you must dyno, they make about 420 right out of the box, right? Something like that.
The 604s?
Yeah.
I don't know what they make. I never look at dyno numbers because everybody asks me dyno numbers, so I just tell them I don't know.
Yeah, I've dyno lots of them, yeah.
But the Smart Tour, Smart Modifieds, after they raced at Hickory, the series took the top 3 motors because the person that was complaining the most about everybody else having more power, his motor actually made 8 more than the other ones, but they're all LS motors.
Oh, they're LSs, eh? Okay.
Yeah,
okay. Yeah.
But Bert was complaining about everybody else, and he was there. They ran all 3 of them at Pro Motor Engines, and his made more than the ones he was complaining about.
Yeah. That's actually a story. I don't know if you guys saw in the background. I have a 68 Z28 that I bought in 1969 when I was 20 years old. And it's the original except for the engine. So when Mike and I went racing again, we bought a stock car that was used and it had a 604 in it. I didn't know the history of it, so I took it to the dyno shop and we dynoed it because I was worried it didn't have enough power. And I probably hear there's only certain guys who can seal them, right? They're certified to build them and seal them. So there's 2 guys in the whole of Ontario can seal them, right? So he was one of the guys. So he builds, half of them probably. And we put it on the dyno. His eyes were popping out of his head. It made 453 horsepower. So the guys that built it, sold it to me, were cheating all this time, right? In fact, Michael Walter would come up to our track and drove that car, actually, like 20 years ago or 15 years ago, something like that now. It's a long time ago now. So I put the motor in the corner because I couldn't use it. I bought a new 604 and put it in the car. And when I bought my Camaro back and restored it, put it in my Camaro. What a great street motor. It's an awesome street. 453 horsepower and idles like a pussycat. And nice street motor anyway. So thank you very much, Forsyth Community College, Brian Hambley, Galen Biggs, for having us here. We had a nice little tour. You guys are lucky to have this guy teaching you. Pay attention, listen and learn, right? And take time to learn. If you learn it, you own it forever. If you memorize it, you'll just pass the test, but you forget the day after, right? Take time to learn and enjoy learning. I mean, Brian and I had a college like this to go to, and we got out of high school. I don't know what we would have been doing anyway, that's for sure. That would have been my choice. So thank you very much for having me. Thank you for watching Gold's Garage. I always forget, please like and subscribe. So thank you very much.